Hello, everyone. Welcome to February's A3D3 Seminar. It's my great pleasure to introduce today Derlev Bluestein. Derlev got his PhD in physics from Harvard, where he developed an approach to quantum computing based on reconfigurable atom arrays and used this for the world's first error-corrected algorithms. And he's now faculty at Caltech, where he's working with other faculty to try and build the world's first useful quantum computer. Um, and he's giving us a talk today on atomic quantum processors and the error correction frontier. So, Dolev.
Thank you so much. And thank you very much for the invitation. Okay, let me just reorient things. Okay, can you see my screen?
Yeah.
Okay, great. So please feel free to interrupt with questions at any point. For starters, so this will be a talk about quantum computing. And as I will mention, one of the central topics right now in modern quantum computing is the development of quantum error correction. And we are seeing the use of AI broadly in this goal, both on more theoretical aspects like discovering new types of error correction codes or using it for improved decoding, to even using AI to optimize experimental performance, etc. So AI is so deeply embedded in terms, or at least we're exploring it quite widely in the various things that we do, that I'm not even pointing it out so explicitly. So I would encourage people to interact with any questions, both about the quantum computing or the use of AI, wherever it can be helpful. So, okay, with that, I'll tell you about work that I did primarily during my PhD, but that I'm continuing with other faculty at Caltech. And broadly, this all takes place in this broader field of quantum science and technology, where we're trying to harness superposition and entanglement for new types of scientific and technological applications. And whereas in classical computers, you do operations on bits that are 0, 1, as we know with quantum computers, you can have qubits that are 0 and 1 at the same time, and then you do operations on the qubits. And if you have n qubits, they can be in exponentially many states at once, and this can give you exponential computational power to study new quantum phenomena or new types of computational algorithms, if you're very clever with how you use this very large Hilbert space. And there are broad applications of these tools, ranging from high energy and cosmology to material science to quantum chemistry. And broadly, to be honest, we're still not entirely sure exactly what we're going to use quantum computers for in the future. But I'll make a perhaps somewhat controversial claim and say that I think quantum mechanics is one of, if not the most surprising thing humans have ever discovered. And it's hard to see our study of quantum mechanics ever going away. And it's hard to imagine a world in which quantum computers are not powerful tools for studying quantum mechanics. And it's such an exciting time that we now get to build this new type of technology to explore these new scientific frontiers. And it's been an exciting recent decade in the field. In the 2010s, we were exploring small-scale quantum computations with physical qubits. And when I say physical qubits, I mean atoms, ions, defects, superconducting qubits, and so on, two-level systems that encode a unit of information. But what started to happen is that we got better and better control over these systems and started to really use them for quantum discovery, where you can put all these quantum systems together, all these physical qubits, these atoms, and study new types of physical phenomena. And we've learned a lot from that. And AI has also played a large role in, for example, discovering new phases of matter from very complex data sets. Although this won't be in my talk, but it's some of the work that we've done. And then the other, which will be the focus of this talk, is that of the error correction frontier, where our control of these systems has gotten so good that we've been able to start entangling these physical qubits into what I would call error-corrected logical qubits, and start to do some of the first logical operations and gates. And broadly, fighting decoherence is the central challenge in attaining large-scale quantum computation. And quantum error correction is the only known realistic route that we have to date to suppress gate errors from the level that they're at with physical qubits at the scale of roughly 10 to the minus 3 to the levels required for useful algorithms, which is at the scale of 10 to the minus 10. And it's in fact so fundamental that before error correction was invented, people thought quantum computing would just be fundamentally impossible. The reason for that is actually quite deep. I mean, broadly, quantum information is fundamentally harder to store and operate on. If you have classical bits, like a classical bit 0, and you interact it with the environment, for example, I have a bit 0 here, we all take pictures of it, then it gets copied redundantly. And in some senses, by interactions with the environment, it gets more redundantly stored and protected. But what we know is that with a quantum state psi, if we take a picture of it, then it collapses probabilistically into either 0 or 1, and it experiences this decoherence event. That's one way in which we can already see quantum bits are very different than classical bits in terms of their storage, but also in terms of doing operations. You could imagine trying to set up a quantum computer as a chain of interacting spins that are all interacting with a very precisely tuned interaction energy J. And this computation might give you something that you're interested in, but what happens if J goes to J plus epsilon? Well, we know that then you can go into a chaotically very different state, and the state of your quantum computer will be completely different. And this is not unique to quantum mechanics. It's also true in the classical domain, where analog classical computers, for example, if I have a voltage and it can be 0.4372 ... volts, it can be, it has a lot of representation power because it's continuous, but we don't use those that much because we can't correct their errors compared to digital computers that are made out of these classically robust bits, where if you have little voltage fluctuations around 0 or 1, that still, erases their history when you just call it 1 or 0, and you become robust to errors and robust to imperfections. And this seems at odds with what we get from quantum computing, where we have, for example, block spheres that have 0 and 1, and we have this continuous and analog rotations that seem intrinsically sensitive to these imperfections. So broadly, we need some type of way to correct errors. And remarkably, it's physically possible, but it works quite differently than classical error correction. In classical error correction, what you would do is you would take a bit 0 and then you would copy it, for example, 3 times. And now if you look at these 3 bits and you see that one of them flips to 1, then you can do majority voting and return to your initial state. But quantum error correction has some conceptual challenges. One is that due to the no cloning theorem, you can't actually copy quantum information. So already this part doesn't work. The other is, how do you check for error without collapsing the state? Because as we just discussed, if you look at the system, you will project it probabilistically. So remarkably, it is possible to do quantum error correction. And the way that it works is you use entanglement to take a single logical qubit that you're interested in and then delocalize it across many individual physical qubits by storing this information in the entanglement between these many qubits. And by being delocalized, this logical qubit degree of freedom becomes hard to accidentally manipulate. And although we can't measure individual qubits without collapsing the state, remarkably, we can measure products of qubits, or so-called stabilizer checks, in order to detect errors while preserving the encoded information. And this is quite remarkable. And it's interesting to go back to the beginning of the field when Shor invented the factoring algorithm, and then he got challenged very publicly by Landauer, saying that you were describing the analog computation. We know we can't correct analog computers. What's new here? And Shor's response was that although the computation is analog, the errors are digital. And it's really due to the wave-particle duality that we actually can use quantum computers in their very powerful, almost analog-like mode on the logical level, but then we can correct them on the physical level as if they're digital systems. And so we can get the robustness of digital computers while still getting the immensely powerful computation aspects of quantum computing. And that's quite amazing. And it's at the forefront of what actually allows us to do powerful quantum computations in the future. A classic example of this is that of the Kitaev toric code. And the way that this works is you have an array of qubits on a two-dimensional lattice. Each dot here is a qubit, and here the lattice has periodic boundaries on a torus. And the checks are products of x's and z's on plaquettes and vertices. And the error-free state of the system is the superposition state, where all x and z checks, these four-body products, are simultaneously equal to +1. And in this state, we can read off the logical information just by looking at the vertically and horizontally propagating X logical and Z logical strings in the system. Now, what happens is that if you have a physical qubit error, for example, a bit flip X error on this qubit here, then now when you're measuring the stabilizer checks, you'll see that these two Z checks both light up as -1. They'll give you a flag. And without revealing what that state of that qubit is, you can infer that there was an error there. This inference process, we call it decoding. It's one of the places where we've been using machine learning techniques. And then once you infer that the error is there, you can undo it in the system, either in the hardware or just in your mind. And remarkably, what happens is that as the lattice size increases, or the code distance d, which is the linear dimension of the system, we get more opportunities for errors, but we also get more checks. And this leads to a sort of threshold behavior where the logical error probability can, in principle, be exponentially suppressed as long as you're below some characteristic threshold, which is only at the scale of roughly 1%. And existing systems have already surpassed this by quite some margins, and it starts to now offer a realistic route to getting to extremely small errors just by increasing the code distance. And although this was a very long time ago, it was really the theoretical breakthrough of quantum error correction in the 90s that allowed the field of quantum computing to take off, because that's when people realized that this is actually a conceptually new type of computer where you get this analog type computation power, but you get digital-like robustness due to the wave-particle duality. And it has been understood since the beginning that we will eventually need to switch to performing algorithms with logical qubits instead of with physical qubits. That all sounds great, but that being said, quantum error correction is really hard. And if you look in the literature, what you would find is that optimistic estimates for the resources required for large-scale problems looks like having, for example, millions of physical qubits to achieve thousands of logical qubits with logical error rates of 10 to the minus 10 and below. And that's a lot of qubits. And that's been hard in the field in a way that's been greatly compounded by the way that these early generation quantum computing systems have been built, where in our classical systems, what we've gotten very good at doing is taking something at the scale of 1,000 wires to control billions of bits. In our quantum systems, we have so far, at least until the past few years, been building them in a way that we have several wires for each qubit, and then now are trying to essentially use brute force to scale up the system. And so one central challenge has been that this wire problem poses a significant challenge to large-scale control. A second key challenge is that once this logical qubit is delocalized, it also becomes very hard for us to do operations on it because now it's hidden in all of these delocalized degrees of freedom. So until several years ago, the large overheads and complexity of actually doing operations on logical qubits had so far focused studies in the field to 1 or 2 logical qubits and gates. And what I will tell you about today is an approach that we developed during my PhD. We refer to as these reconfigurable atom arrays, and how we've used that for doing quantum computing and as well as quantum error correction. And what the system looks like is we have neutral atoms trapped inside of optical tweezers. These are tightly focused beams of light, where the atom is attracted to the point of highest intensity inside of this optical tweezer. And then this snags an individual atom. We use rubidium atoms. And then what happens is that we can entangle the atoms by zapping them to these so-called Rydberg states. We just take a very finely tuned laser frequency, and this almost ionizes the atom. It takes it into a very, very high-lying orbital state where it starts to strongly interact with the other atoms. And then we can store the quantum information inside of this long-lived hyperfine qubit state that has coherence times on the scale of seconds. And in fact, the coherence is so long that we can even move the atoms around in the middle of the computation. And this ends up giving us 2 very unique opportunities. One is non-local connectivity, which, as it turns out, is extremely useful for quantum error correction. And the second is that of parallel and efficient classical control. This is something that I developed quite closely very late at night with Harry Levine, and he is also starting a lab at Berkeley, and I would strongly, Harry's great. I would strongly advise people to reach out to him if you ever cross paths. Okay. Let me take a quick pause to see if there's any questions. Also drink some coffee and water. Any questions? Okay, please interrupt anytime with questions. I love questions. So what this system looks like for quantum computing is as this movie here. This is slowed down by 10,000 times. the atoms are moving around the quantum computer, and then each dot here, these are real camera pictures that we measure via scattering off of the atoms. And there are 16 data qubits here that are fixed in fixed in tweezers. And we have another 8 ancillary atoms that are moving across the system, measuring these stabilizer checks. And here they move with periodic boundaries, and this creates the so-called toric code on a torus with periodic boundaries. And what you can see is that we move the atoms, pulse global lasers, and that's the essence of how we program these quantum circuits. And as I keep mentioning, efficient classical control is really at the center of how we think about controlling these systems. And broadly, when you work with these atomic systems, something that becomes clear extremely quickly is that there's tons of atoms. Numbers of atoms is never the limitation. Here in our, humble MOT that we had during my PhD, which was not impressive at all, at least the MOT was not impressive, we had on the scale of 10 million atoms trapped in a millimeter size region. And the takeaway from this is that cold and identical neutral atom qubits are essentially unlimited, and the key challenge is just how to control them. And here, optical multiplexing plays a very big role, where we take, for example, a single laser beam and then shoot it onto a single optical device, such as a spatial light modulator. And what this allows us to do, is by imprinting a programmable phase profile, we can then create, thousands of tweezers that here, several years ago, we were capturing roughly 1,000 atoms with. And then we have another set of optical tweezers. These are acousto-optic deflectors, and these use frequency multiplexing to just with 2 voltage waveforms, one in X and one in Y, we can do parallel sorting of the array and parallel motions of the array in order to arrange this initial configuration of atoms into a defect-free grid. And we've made many, many types of pictures of this over the years. Here is a Mario that we made many years ago. One day we'll have quantum computer games that are made with single atoms. That's how we lay out the processor. But then we also want to entangle the atoms in order to turn them into a quantum computer. And as mentioned, here what we do is we excite the atoms to a high-lying orbital state, Rydberg state of n equals 50 to 70 or so, where the atom grows substantially in size at the scale of hundreds of nanometers. And this makes it pick up a large dipole, or it can pick up a large second-order dipole via van der Waals interaction. And what that corresponds to now, what's so special is if we put 2 atoms next to each other, and then we simultaneously try to excite them to the Rydberg state, which we do in our system with a 2-laser process, 420 and 1013 nanometers, then they'll both try to go to the Rydberg state, but this picks up a very strong van der Waals interaction, and that prevents both atoms from getting excited. And quite simply, this Rydberg blockade mechanism, where only one atom can get excited, leads to entanglement in a way that's robust and insensitive to the interaction, specific interaction strength between the atoms. So we have 2 atoms in G, we simultaneously try to excite them both to the Rydberg state, and then they compete who gets to go to the Rydberg state, and then they go into an entangled superposition of Rydberg ground plus ground Rydberg. And just like that, you generate entanglement. And again, as mentioned, we can use these tools here in order to program these quantum circuits just using global pulses and using blockades. So we just move the atoms around using our optical multiplexing techniques, pulse the laser, and if 2 atoms are next to each other, they entangle, and if they're not next to each other, they don't entangle. And just using the simple programming techniques, we can here, for example, create logical qubits. Here are the first quantum circuits that we did in 2022, just with these simple movements and laser pulses and optical multiplexing control. We'll take a quick pause to see if there's any questions. Okay. So that's how we program this quantum computing apparatus. But then we would also like to control logical qubits. And what you can start to see, and what we started to get excited about as a pretty exciting opportunity, is that what this really enables now, this system, is doing efficient control not only over physical qubits, but actually over logical qubits. Where imagine if you want to program a quantum computer, but now on the logical qubit level, And you have an array of surface codes, which are, a type of logical qubit very similar to this Tor code that we've been discussing. And let's say you want to do a single qubit gate, a single logical qubit gate on each individual surface code. Then what it turns out you don't have to do is you don't have to do a unique pulse onto each individual physical qubit. You just have to take this one big beam to do, for example, a Hadamard gate, and just do that exact same operation on all of the individual physical qubits of the block. And so just by using one big beam, you can effectively eliminate this one big block of qubits, and it will do this one logical operation. And remarkably, we can also do this for 2-qubit gates, where we take these 2 grids of qubits, interlace them with each other, and then just do a single global pulse of our entangling laser. And then in just a single parallel step, we can get transversal entangling logic between these 2 blocks, where by just doing pairwise entanglement between all of the individual twins, you get entanglement between the logical qubit degrees of freedom. And this is an enormous simplification. And if you look at some of these early works from Peter Shor, where fault-tolerant computing was first invented, he has this somewhat funny comment about how this operation is easily accomplished by elementary gates, as it is a bitwise operation. And he means from the perspective that if you do these bitwise operations, it's intrinsically fault-tolerant, meaning that errors can't spread within the block because you're just doing gates between blocks. But also from an experimental perspective, it's enormously simple. You just take these 2 blocks, put them on top of each other, pulse this one big laser. And what this now allows you to do is you can start programming quantum processors on the logical qubit level. And here was our first generation logical qubit processor that we developed during my PhD, where you have 3 separate zones: a storage zone, an entangling zone, and a readout zone. The logical qubits can be stored for long times idly in the storage zone due to the long coherence times in the system. And then if you want to entangle 2 logical qubits, you take these 2 blocks, move them into the entangling zone, do a single global pulse. And you can also move the qubits to a separate readout zone to measure some of the qubits in the middle of the circuit and proceed with the computation while also getting information out of the system. And we've used this to do a variety of different error correction codes and circuits in many different contexts. Here's the first one we ever did in terms of programming the first error corrected quantum algorithms. This, one of the simplest algorithms you can do is make a so-called Schrodinger cat state or GHZ state, which looks like 0, 0, 0, 0 plus 1, 1, 1, 1, but now on the logical qubit level. And the way that we're doing that is we have these 10 so-called color code logical qubit blocks. They're very similar to the surface and Tor codes that we've been discussing with some slightly different properties. And this movie shows how we do this with this parallel control. So you have these 10 blocks, and then in the first 1, 2, 3 steps, we create these 10 color code logical qubits. We then entangle half of them transversally with the other half and move them to a separate storage region. And then we pick up 2 of the logical qubit blocks and start to slide them around the system in order to make this programmable so-called Clifford circuit for creating this logical GHZ state. And just with these simple approaches, we can create this programmable logical qubit circuit. That's one of the things we studied. Another thing that we studied is how well we can entangle 2 of the logical qubits. And in particular, what we did here is we made 2 surface codes of here distance 3, meaning the lattice is 3 by 3. We measured the stabilizers just once using a set of ancillas, and we moved the ancillas away to the side, do a gate between the 2 surface codes to entangle them, and then measure the Bell state that results from this entanglement. And as mentioned earlier, a key property of error correction is that operations should improve as you increase the size of the system. We studied this here from distance 3 to distance 5 to distance 7, which at the time were the largest error correction codes made, as well as certainly the largest that were entangled. And what we saw is that we can very slightly improve the gate performance as we increase the size of the code. So as a reminder, we're trying to get to 10 to the minus 10. So this is not 10 to the minus 10. This is like at the scale of 10 to the minus 2. But it was the first time that we actually saw ourselves getting below this threshold, also for an entangling operation. And there'll be more data later in the talk studying this threshold behavior. But the other thing that we learned is how important this decoding algorithm is to practical operation of these error correction systems, where if you use the conventional decoding approaches, where you do this inference process within 2 individual blocks, then there's actually some pretty fundamental limits in terms of so-called fault tolerance of the system, in terms of how much error correction you have to do. But if you can actually do what we call a correlated decoding approach, and this was spearheaded by a theorist who was spearheading a lot of this neutral atom error correction theory, Madeleine Kane. Then with correlated decoding, by looking between the different blocks and using more information by doing inference on this block in a way that also depends on what you're doing on this block, we are able to greatly improve the performance. And not only for this experiment, but what we've learned is that this actually broadly applies for doing universal computation. And the implemented protocol we had here, we developed for doing these experiments, allowed us to reduce what is typically assumed to have to do d rounds of error correction every time you do a logic gate. We say that you can reduce that to on the scale of 1 round or slightly below for doing universal computation. And so in terms of science of error correction we've learned in the lab, one of the things that we've learned that's quite central is that when you're performing logical algorithms, instead of considering individual logical qubits, you really want to consider quantum algorithms as a whole. That's one of the key scientific lessons we learned from these first experiments. Another one is the error correcting code, algorithm, and hardware all have quite funny constraints. And broadly, it's really quite important to do what I would call a type of fault-tolerant compiling, where you consider, there's such a huge zoo of error correction codes, and there's a huge zoo of algorithm routines, as well as different ways to combine with the hardware. And it's really an art form where you need to consider all three at once, and considering them in segmented ways tends to not quite find the right solution. And one of the aspects of that that's quite fundamental is that with error correction codes, you can only do a discrete gate set. For example, with the surface code, you can only do Hadamard, which is a 90-degree rotation, an S gate, which is a 90-degree rotation around the z-axis, and a C0 gate, and something like a non-Clifford gate, which is something like a 45-degree rotation on the z-axis of the block sphere, which is needed for universal processing as well as for classically complex simulation. That's actually quite hard to do with these two-dimensional error correcting codes. And it's quite fundamental that with logical qubits, continuous rotations are actually the hardest thing you can do, because it's this like analog type angle. But entanglement is actually very easy, that you can do between two logical degrees of freedom, just by, for example, doing a C0 gate. And this is completely backwards from what we're used to thinking about with our physical qubit systems, where you're used to your experimentalist friends in the lab telling you that, oh, entangling qubits is hard, but we can rotate them however we want. And it starts to show how this is just a completely new type of system, and that we're still learning so many basic things about working with it. So the idea that we had here in order to explore doing efficient fault-tolerant compiling was to do a quantum simulation or a quantum scrambling circuit, but with discrete gates. For this, we actually used three-dimensional codes. They have special properties that actually allowed us to do transversal non-Clifford gates, in particular here, CCZ gates. And what we did here was make 48 logical qubits and then entangle them on hypercubes that are fast scramblers, and did hundreds of logical entangling operations, as well as 48 logical CCZs, which are a powerful type of non-Clifford gate, and studied sampling with the system. And what sampling looks like is you make a very complex many-body wave function on your system, and then you compare it to precise simulations you do, and then you see how well they line up, and this tells you about the fidelity of your experiment. And what we saw in these first logical algorithms that we were doing here is that we were able to do quite a bit better with these logical qubit codes than we were able to do with physical qubits. Importantly, for this experiment in particular, not the other ones that I've been showing, we also used some post-selection. So we're actually throwing out quite a lot of data at the scale where we're exploring many logical qubits. But it was one of the first examples we started to see where, for interesting tasks like simulating this quantum scrambling, we were actually able to do quite a bit better job doing it precisely with our error correction systems, as opposed to with just raw physical qubits. And I want to zoom in a little bit into the data. It's really true that looking at these error correction codes and the data they produce is quite striking. And it looks quite different than things we're used to seeing with our physical qubits. And here is an example sampling data set where we're looking at a 12 logical qubit system. So there's 2 to the 12 possibilities. And we're doing this complex circuit, and we're looking at all the different components of the wave function that pop up. And what you see is that everywhere that there's a theoretical peak, there's a experimental peak that follows. But what's also quite remarkable is if you zoom into even the smallest features, so look at this red arrow here, and you zoom in further and further down to the noise floor of this distribution, where here are these 2 tiny features or these 2 big features here, you can see that still the the error correcting experiment reproduces the shape of the theoretical distribution. And even here, although the fidelity wasn't perfect, you see the heights are not perfectly aligned. Even down to the noise floor, you can reproduce the right features. And it's really this feature that you can do digital and precise creation of many-body entanglement built out of digital building blocks. Coming back to this argument between Shor and Landauer points to this analog type computation, but digital type errors in the system. So that was the first set of experiments that we did exploring error-corrected algorithms in the lab. And we've learned a lot from doing that. So our goal was go do error correction experiments in the lab, do error-corrected algorithms, and see what you learn to guide our direction from there. And the central lesson that I cannot possibly emphasize enough is the importance of parallel control. We did these experiments just as a few PhD students in a lab. And the reason we were able to do that is just because instead of programming complex circuits on hundreds of physical qubits, we're actually programming simple experiments on a handful of logical qubits. And this is an example. This is the first circuit that we did, which is this Schrodinger cat state out of logical qubits, where we are really thinking about just programming the circuit on the logical qubit level. And this has greatly facilitated this exploration of doing logical qubit experiments with neutral atoms. The other is the importance of considering the algorithm as a whole, and here the so-called correlative decoding and algorithmic fault tolerance. We've then pushed much further on a theoretical level and now have ways to reduce, using the techniques that we developed here, reduce the overheads, the time overheads of quantum error correction by a factor of roughly d, which for large scales can be on the scale of roughly 30, just by changing how exactly we're doing this decoding inference, as well as by using these transversal operations. We've learned about the importance of doing fault-tolerant compiling, where we really consider the specific error correction code, the specific algorithm, and how they connect together, as opposed to studying them individually. We learned about how errors get digitized when you do these experiments. And broadly, I think something that we've experienced in a quite substantial way is a transition in the theory that we do to focus algorithms to the study of error correction, as well as focusing the error correction we do to the implementation of algorithms. And we've learned a lot from that whole process. Okay, let me take a quick pause to see if there are any questions. No question is a stupid question. Please ask any questions at all.
Okay, since you allow for stupid questions, I'll chime in.
Excellent.
So no, I just had a roughly okay, I thought you said the coherence time is roughly a second for these states. Is that what I heard?
Yeah.
And then you're moving these atoms around with the lasers, and you're hopping from site to site. And I was just wondering two things. I was just really thinking about like stability and time scale. So you're moving these around. Obviously, I would think you would need to move them around on time scale much less than a second, the coherence time. And then also, does the moving around actually decohere I mean, does it have an effect, or are these pretty robust against movement? And I mean, how many sites do you need to move the atoms around on what time scale? I'm trying to get a feeling of the time scales.
These are excellent questions. So the timescales for movement are typically on the scale of hundreds of microseconds, sometimes to the scale of millisecond. And we move them in these tweezers, and we have atoms spaced by roughly 10 microns in like static grids, and then we have to move to like a new interaction site. You have to move on the scale of 10 microns, and that takes on the scale of hundreds of microseconds, depending on the specific movement implemented. It works quite well, but it is sometimes a little buggy. So you have to get it, you have to engineer what we call spin echo, where you get imperfections in the motion to cancel out by, for example, doing a pipe pulse during the motion, or moving somewhere and then moving back to get the imperfections to cancel. So we have a whole suite of techniques we've developed for that. But broadly, if you debug the system sufficiently, then you just converge back to the coherence time at the scale of a few seconds. And that's what sets the performance. So if you're doing a stabilizer measurement for the error correction and it takes roughly 1 millisecond, and the coherence time is on the scale of several seconds, then it corresponds some error at the scale of 0.1%, which is quite favorable from a threshold perspective for that type of error.
Okay.
Yeah.
Yeah, that makes sense. Yeah, thanks. Thank you.
Yeah, fantastic question. Thank you so much. Anything else? Okay, please feel free to keep chiming in with questions. So that was our first goal. It was poke around with error-corrected algorithms, see what you learn, And then based off of the things that we learned, we then, for our second set of experiments here, tried to systematically study what are all of the different things that you need to do universal fault-tolerant quantum computation, because there's a lot of different things. Sometimes it gets confusing what things are needed, what things are not needed. And by having a clear and crisp understanding, we'll be able to design the architectures of the future processors much better. So two things that we studied here quite carefully. One is operation below the error correction threshold when we do multiple rounds of repeated error correction. And here we saw that we were able to get to roughly a factor of 2 times below the threshold. And here machine learning actually played a central role in doing this decoding process. And then another aspect is we set up the architecture in a way which is compatible with doing universal deep circuit fault-tolerant processing. And in particular, one of the things that we uncovered from an architecture perspective is the role of logical teleportation being central to doing deep circuit and universal processing. And here, we're really cycling the atoms through like a fridge. So the rest of this is a little bit technical, but I want to show some of it anyway. So one of the things that we developed that was quite important for this is the ability to measure our qubits non-destructively. The issue here is that with conventional readout approaches, if you just try to measure the qubit state within the atom, then the imaging light often mixes the spins together. So what we do is we actually kick out the qubit state 1 from the trap, and then we use fluorescence imaging to detect just whether the atom is there or not. And that's robust, but unfortunately you lose half the atoms, so you can't do many measurements on them. With lossless and state-resolved readout, there's multiple benefits. One is that you don't lose the atoms, and then 2 is that you can directly detect if a qubit was lost. And the way we do this here is with a spin-to-position conversion, where we added a one-dimensional optical lattice to the system, and then we move the atoms, where we move the tweezer, and then there's a pinned tweezer, where qubit state 0 stays pinned by the sharp walls of the lattice. Qubit state 1 doesn't see the lattice, and it just moves right through, and then separates the 2 spin states. And then here we can see the atoms Rabi oscillating between left and right. And we have this amazing track record where we explored many different approaches here for non-destructive readout, but somehow the coolest looking technique seems to always be the one that always so works the best. So this was the best technique that we found for doing non-destructive readout so that we can keep using our atoms as well as detecting the loss. And this is quite technical, but I do want to show it because it's quantitatively important. We benchmarked quantitatively how well performing our system is on this classic experiment of doing surface code repeated error correction. And here it's with 4 rounds of error correction. And I think it should also be compared to beautiful recent work by the Google team that had similar performance, but doing many more rounds of the error correction. And here, in particular, by using the machine learning, what we see is that as we increase the code distance, we're actually making the error better by a factor of roughly 2. And if we would have done this experiment in 2019, for example, we were more than a factor of 20 above the threshold, despite the fact that we didn't even know how to do quantum computing with atoms, then it would have gone up by a factor of 20. So the fact that it's now going down, even by a factor of just 2, is a very, very good sign. It means that we're actually starting to surpass these thresholds, and we can actually start to envision getting to exponentially low errors. The error budget that we characterize for the system is as follows. And broadly, based off of various improvements that are currently happening, I think it's quite likely that being a factor of roughly 5 times below the threshold is something that will happen quite soon. And that will already be at the level that is needed for doing large-scale processing. We also saw a bunch of other things. We carefully characterized the error distribution in the system, didn't see any evidence of, for example, large-scale correlated errors. We saw that leakage to other levels was actually quite well managed, and in particular, using this lattice for detecting loss seemed to capture a majority of any type of leakage type effects. And we in the methods of this paper discuss a path for how to get to 5 to 10 times below the threshold by making quite straightforward improvements, which are ongoing. So broadly, from doing these quantitative experiments, we see here that we're below the threshold. We see a pretty clear path to getting to the required levels below the threshold. And we did not really see any surprises, with the caveat that one of the things that we learned doing these highly quantitative experiments is that it's really just important to do a lot of debugging. in order to get these atomic systems to reach their theoretical spec. We're always able to get these atomic systems to reach their theoretical spec that's given, for example, by the laser power, etc. But there's always some type of random thing going wrong, like magnetic field noise, the move being imperfect, etc. And it's all about just debugging in order to get it to the level that you want. So that was studying how far we are below the threshold. This is more details now on our architecture for doing deep circuit processing. So as mentioned before, we have the storage zone, entangling zone, and the readout zone. We also have a reservoir here for replenishing lost atoms. And you should really think about these error-corrected computers. They're both the computer on the logical level, but on the physical level, they're a fridge. There's lots of imperfections that build up on the physical level, both bit flip errors, but also, for example, atomic heating, atomic loss. And these are all different types of entropy that you need to remove in order to keep the entropy constant in the system. And one of the things that we've learned on a somewhat theoretical level and practical level is that when you're doing all these transversal gates, teleportation is really the key unit that you should be thinking about for this logical processing. It natively removes the errors in the system and it also serves for doing loss detection. It also enables realizing magic. Magic is another word for the so-called non-Clifford operations. And here to study this, what we did is we made 16 steam codes or color codes at a time and entangled them in up to 27 time layers and did several hundred logical teleportations this way. And this is a movie that shows how this works. So we take atoms, move them into the entangling zone, and then we create them into these color codes here, similar to the movie I showed you earlier. Then we entangle these color codes into a cluster state. We entangle with the previous group into a two-dimensional cluster state now in the time direction. We then take these atoms and split them using the lattice. And now you can detect whether the atom went up or down. And this is a kind of Stern-Gerlach type approach that allows you to detect the qubit state deterministically, inspired by Dave Weiss's group. And we put the atoms back into their original position and then repeat the whole thing over again. So that's one cycle. These poor atoms, we made them go through 27 cycles in order to make these 2D cluster states here that are in the space and time direction with these several hundred logical teleportations. Here I'm showing this for steam codes, but we also did this for high rate 1664 codes. You can encode many more logical qubits sometimes in so-called high rate codes, and these high rate codes are actually very well suited for doing this logical teleportation process as well. So this is what these poor atoms are going through in order to give us this data set. They're just cycling through the system. And the beauty of this approach is the logical information keeps teleporting down the circuit, also doing logical operations as it teleports, but the physical information is always refreshed and entropy is always removed from the system. This is sort of the engine and refrigerator behind the processor. So this is just roughly half of this recent paper that we have that's detailed here. An archive was recently published in Nature. We also studied a lot of the core physical mechanisms required for this universal fault-tolerant processing, such as entropy removal. So here we quantified how well it works, but here we also studied some of the key physical principles where we see, for example, if you have continuous imperfections like analog angle imperfections or globally correlated imperfections, we see that doing the stabilizer measurement accounts quite well for that due to two physical mechanisms. One is the Zeno effect that quadratically projects errors. The other is tracking errors and removing entropy from the system. We also studied the role of fault-tolerant logic in the presence of entropy removal, where we did many entangling gates between two logical qubits and interspersed that with error correction removal, entropy removal, and then studied the role of that for doing fault-tolerant processing. And we also studied how to do arbitrary unitary operations on this logical qubit, where you have to take, this discrete gate set and then patch it into doing these arbitrary analog angles. And we see that we can, for example, using a logarithmic number of gates, achieve some desired precision of angle on our logical qubit block sphere. And you see here all of these dots are the different states that we made in a digital robust way for these logical qubits. And broadly, the takeaway from these range of experiments is that we have a simplified framework and architectural understanding for achieving all the ingredients that we need for scalable, i.e. logarithmic overhead, realization of doing arbitrary quantum algorithms. And we studied a ton of different things in this work in both the main text and methods, which I would encourage people to read in case they're interested, ranging from generalized techniques for syndrome extraction, erasure information and machine learning for decoding, lattice surgery and transversal operations for realizing the logic, this transversal unitary synthesis and code switching, as well as high rate encodings and deep circuits with dozens of logical qubits and hundreds of logical teleportations. And broadly, I think that those set of experiments really helped us understand least in my mind, it really helped clarify things in terms of what things do we and don't we need for doing universal fault-tolerant processing. And this also gives significant improvements and simplifications to the architecture design. Another thing which is really fun is that by being able to reuse these atoms, we can also start to use them for much faster atomic physics experiments. So this is how fast we get data now in the lab for doing, for example, Rabi oscillations. For an atomic physicist, this is maybe very impressive. It might not be as impressive for something like superconducting qubits, but you can see here real-time traces of Rabi curves in the lab. And you can see that we're going to get just way more data now, roughly by a factor of 2 orders of magnitude faster data rate by using these new quantum information processing tools for improving our atomic physics experiments. And this can also actually really be at the basis of using machine learning for improving the system performance, because now we're just going to get so much more data. Similarly, in parallel experiments that we did in the so-called Atom Array 2 team, where I really want to acknowledge this Atom Array 2 team worked so super hard on these beautiful experiments at Harvard. And here, what we did is we studied continuous operation of 3,000 atomic qubits in the system in a very similar zoned architecture, but now with a reservoir that's being continuously replenished with a lattice and with replenishment rates that are orders of magnitude higher than what we need, as seen by our other set of experiments. And you can see here what we did is keep systems alive of 3,000 qubits continuously on the scale of hours. And you can see how this combines here with this fault-tolerant processing architecture that I've been overviewing for you. So it's quite an exciting frontier right now for neutral atoms and for error correction. The rate of progress with neutral atoms, I think, has been quite remarkable. Scaling to larger system sizes, for example, systems at the scale of 6,000 qubits in Caltech's labs, different types of atomic species, new types of optical addressing. It's quite amazing the rate of progress that is happening with neutral atoms. And at this point, I think there's nothing that anyone can really do to slow it down. I think that the tools are conceptually so much simpler than, for example, needing a huge fab facility. And I think that there will be just so much progress across the field in the coming years from so many different angles. And I'm very excited to see what happens. And the other thing is that I think in the past 2 years, you can now really start to say that it's extremely clear that quantum error correction works. And some of these references are slightly out of date, but you can see here what I was really struck by in the end of 2024 and throughout 2025 is just how rapid the progress has been across so many different systems, from superconducting qubits, trapped ions, academic labs, industry labs, neutral atoms, all of the above. And I think it's quite clear that we've crossed some type of inflection point. It's also been a remarkable exchange of ideas between these various different systems. I think it should be quite an exciting next few years. So that is the end of my talk. I'd like to acknowledge a handful of people. First off, I would like to start by acknowledging the amazing colleagues I had while I was at Harvard. This is the so-called Atom Array team. The team has changed over time, but in particular, well, first off, I'd really like to acknowledge Simon, who is one of my closest collaborators during all of these experiments. But lastly, I also really want to highlight Sasha, who worked extremely hard on these recent experiments for doing logical qubit fault-tolerant architecture. She's also extremely sharp. You should watch out for what she'll do next. And finally, we are doing much more research now at Caltech, and our research group would love to collaborate. So thank you. That is the end of my talk, and I am open for questions.
Great, Dale. Thank you. That was really good. So we've got a few minutes for questions from folks.
Thank you, Dale, for this presentation of very exciting progress. And it's really amazing to see this error correction works through the demonstrations. And you talk about the machine learning decoding application is one of the key to achieve this. Could you say a few more words about what's the architecture of the machine learning and what's the constraint for that right now? Is that the limit to the scalability if you want to go even bigger large qubits? Thank you.
Fantastic question. So in these first experiments, what we did was a fully connected neural network because it was simple, and its performance was great because it was just fully connected and we had a lot of training data. It was a small system, but it's not scalable. So it's not scalable to doing algorithms, it's not scalable to changing the circuit, and it's not scalable to larger sizes. So since then at Caltech, we have been doing much more work. I'm not ready to fully present on it, but the highlight is that we're exploring hybrid approaches between algorithmic and machine learning, and we see that we're able to, with this more hybrid type approaches, get both the speed of algorithmic approaches like matching, but get the performance that we're able to get here with machine learning, as well as, for example, capturing one of the things that machine learning is very good at doing is capturing small experimental variations locally, as well as, for example, imperfections like loss. And we've been exploring this for improving the performance. So, okay, let me say it in another way. I am at this point convinced we will use machine learning in the future of large-scale error correction. I'm also convinced that one wants to be clever about how one does it before we start going and like really brute forcing all the knobs.
And do you do reinforcement learning? You collect in data and retrain the model or fine-tune the model?
That's right. That's what we did here. So we have this fully connected neural net, and we, are essentially classifying cat or dog, and then we reward the model when it does correctly. And in that way, improve the performance. We're also exploring now a whole host of different types of methods that we could discuss more offline.
Yeah, great. Again, this is really exciting. And by the way, you show my real video earlier. That's the real data, right?
That's real data. Yeah, all
Wow.
of the movies are really pictures of atoms.
Right.
That's the other thing, is that this is just these experiments, they're like playing video games. I mean, it's like amazing. Like people give you money to go, maybe I shouldn't be saying this in a recorded talk, but it really feels like
We'll edit
playing
it out.
video games. No,
Yeah,
but it's amazing. I mean, it's like and then when we program circuits in the lab, you see where the atoms are, you put the atoms next to each other, and then if they're next to each other, they entangle. It's that easy.
Mhm.
So a lot goes into it, but yeah, it's amazingly fun.
Yeah, this just remind me like all this AI revolution we're talking about, all those GPU, they are all started with the people want to play video game.
That's a good point. Yeah, that's great.
Yeah, I think you just said, yeah, I assume actually the red ovals are annotated, unfortunately, right, in your videos.
That's right.
It just shows that it's an entangled pair, right? You just annotated this. There's
That's
some
right.
entangled.
Yeah.
Okay.
Yeah, you can see it here. Yeah.
Yeah. So you talked about machine learning just now for error correction itself, but I think there's also you mentioned a point that I've also tried to make with many colleagues about the co-design aspect between the error correction strategy and the algorithm itself and the
Yeah.
hardware. So it's a triad. See, that's where I think have you explored? I mean, I kind of wonder, you must have studied a specific algorithm for all these results.
Mhm.
And then immediately you wonder about the co-design. Well, if you were to do a different algorithm, would the
Yeah.
whole apple cart be upended and you'd start from scratch? I'm sure not. But how you go from, I mean, that's one of the things machine learning does, is it interpolates, right? It goes from one scenario and maps it to
Yeah.
another. So I guess, have you explored the co-design space of how you can take your strategy and move away from the default algorithm to like a broader class of algorithms, and how much you have to do differently?
So very preliminarily, so at the scale that I don't have any concrete conclusions to share for that yet, although I completely agree with you. I mean, I think that this is like for both finding new codes and improving algorithm compilations and improving how the codes fit with the algorithm compilations. I think at this point, our thinking is just machine learning everything. I mean, machine learning is amazing for these types of things.
Because there's no other way I don't see any way of human in the loop co-design capturing the complexity of the error correction needs for the algorithms.
Yeah.
Unless there's something universal, but it seems like a very kind of complex mapping. Yeah.
Yeah, I mean, I'll say, okay, one thing I will say is that sometimes when you just black box optimize these systems, you don't get the right answer. And it's not because it gives you a wrong answer, it's because for something to work in practice, so again, we're doing this with like a few PhD students, and it's amazing that it's possible. But the reason it works is because it's elegant. And so far, I would say it's really an art form of the human. So I have like 100 different PowerPoint slides on my, or like PowerPoint files on my computer of different circuits, which are like this code, we're gonna do the atoms moving in this way. And it's like you just go and search for something that's elegant. And that I think machine learning could do much better. I think one of the challenges will be how to describe to the AI the right cost function of what it looks like for something to be elegant and not just like optimized, for example, for reducing qubit numbers or numbers of gates. But I completely agree. I mean, I think that it's broadly we're now moving. So here I've overviewed both basic understanding of the error-corrected algorithms as well as now fundamental what do you need in an architecture. But it doesn't mean the architecture is designed. Now it's like a whole new engineering discipline. And I think AI is very powerful for that because it's like an art form. It's design. So I don't claim to have the right answer yet, but I think that that's something that would be extremely interesting.
But I think your point, and Matthew's about yeah, we could make sure other people have time, but like, I think your point is that the PhDs in the loop was critical to get to what we're able to do. In other words, any sort of black box optimization will fail. But I think there's like a meta part, which going from where you are to a more of a general purpose error correcting code for
Yeah,
general, that's the part that probably it's machine learning might play a role in.
I agree. I also think
Okay.
these machine learning tools have gotten so powerful, and they're clearly getting more powerful that currently I think about them as being it's like another researcher you're working with almost. And this researcher is kind of particular. You know, you have to work with them in a very particular way. But they're kind of right now at that same level where it's not yet like, okay, anything the AI tells us to do, we're doing it. But it's like a trusted colleague that's part of the process. That's the way it currently is working for us.
Okay, great. We're at the hour. So thank you very much again, Dolev. This has been excellent. And I encourage folks to follow up with Dolev if they want more discussion. He certainly seems very open to it. Next month's A3D3 seminar will be the multi-messenger astronomy group reporting on the work that they've been doing. So I'll send out details of that in the next couple of weeks. Otherwise, thanks everyone.
Thank you.
Okay, bye.
Give great talk.